this is Chycho. Welcome to another ASMR math video. Now, what I wanted to do in this video is do a sort of a very quick introduction to logarithmic functions. Okay, and I do plan on creating a whole playlist, whole series, sort of a module for logs, just the way we're doing for trigonometry right now, right? Because we've been, working on putting together a trig playlist. We've been working on putting together a standalone module for trigonometry, and about halfway through that series right now, and we'll definitely get that done, hopefully, by the time summer rolls around, right? Definitely in 2016, and I will most likely, hopefully, get to a full series on logarithms by the end of 2016 as well. But I've had a lot of requests to do this video, to put together a video for logs, and logs is one of the topics in grade 12 mathematics in my part of the world that people encounter, and it's one of the ones that gives people a hard time. It's the second one, really. The first one that really ends up destroying people, really just throws people for a loop, is trigonometry, which is why I decided for ASMR math to start putting together the playlists for that, to start putting together modules for that, starting with trigonometry, and logs I'm going to do next, because that's the one that people have a hard time with. Okay, so consider this video sort of a teaser for what will be coming up for the logs playlist. Okay, and we're sort of going to run through it, and one of the things with logarithms is the concept of logs. It's sort of a new way of thinking about functions or approaching mathematics, and sort of a new concept, which is basically taking the inverses of exponential functions, right? And I think what's really important to do with logs, to be able to understand, so you could have a nice grasp of what logarithms are, is to have a visualization of what logs are. Okay, and mathematics is incredibly visual, right? It's basically us taking a look at the world and trying to understand it through the language of mathematics, right? Trying to put systems, things that we see, either taking measurements and doing exact calculations, or taking some kind of system, something that's happening in the world, and putting an equation to it, putting a function to it, and trying to represent that system through a function, right? And logarithms is one of those systems, is one of those things that pops up. Okay, so the first thing we need to do with logs is talk about exponentials. And we've talked about how to what exponentials are, powers and radicals and stuff, in series 2, but we didn't really delve into what exponential functions are, and that's what we're going to do right now. We're going to take a look at one of the most basic rudimentary exponential functions that we have, and then we're going to take a look at how that is related to logarithms. Okay, and it's a pretty cool little trick, little concept that we do in mathematics. And once you understand this, you'll be able to branch off from this. Okay, because this concept of finding inverses of functions, in this case we're going to find the inverse of a exponential function, which leads us to a logarithmic function. Once you start doing this, you can do this for any type of function that you want. Okay, so first of all, let's put together a graph, or Cartesian coordinate system. I'm going to put an x and y axis together, and put an exponential function on this graph. Okay, so let's do this. Let's find our, where we're gonna, we do need a little bit of room for writing, right? So let's put this thing here. Yeah, let's do this here. We'll put our 0, 0 about here. Okay, so that's going to be our 0, 0 point. And since I'm not good at drawing straight lines, let's use this guy. Just a piece of cardboard, right? What is this? Drop again. I got this through a package I got from buying comic books, right? So I have a lot of these little cardboard pieces laying around. So what do we got? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Let's take it up to 6. So let's do one more. And this one, let's take up to 6 as well. This thing's not perfectly straight, so I do have a better thing. Do we have a better thing? Yes, we do. I got this guy over here. Let's just take the backing board for a comic book, right? That's better. 1, 2, 3, 4, 5, 6. Is that good enough? That's good enough. Right. So we got our Cartesian coordinate system, and we don't need a large graph. We just want to get a really quick visualization of this, right? So what we're going to do on this graph, we're going to graph an exponential function. We're going to graph y is equal to 2 to the power of x. Okay. So let's put this guy here. Let's do this in a different color pen. Let's do this in black, I guess. Let's check it out. This is a good black. Sure. Let's say we got the function y is equal to 2 to the power of x. So y, can you see this? How high can it go? Yep, that's good. So let's say we have y is equal to 2 to the power of x. Okay. And we have ways of graphing this, right? And what we're going to do right now, we're just going to graph it using a table of values. Okay, so what we're going to do is we're going to create a table of values for the x and the y. So let's put the x here, and let's put our y here, and let's draw, get a coordinate system, right? Get points for this graph. So all we're going to do is we're going to plug in values for x, and we're going to find out what the y is. Okay, so first of all, what we're going to do is find out what y is when x is equal to 0. And when x is equal to 0, 2 to the power of 0 is equal to 1, right? Stuff that we talked about in series 2 of the language of mathematics, right? This is where the exponent stuff comes in. So when x is 2, y is equal to 1. So each one of these little grid marks we're going to use as 1. So this point is right here. Okay, this is 0 and 1, right? Let's plug in x is equal to 1. When x is equal to 1, 2 to the power of 1 is 2. So when x is 1, y is 2, right? When x is 2, y is going to be 2 squared, which is equal to 4. Right? Exponential grows exponentially really fast, right? So when x is 2, y is 4. 1, 2, 3, 4. Okay. If I go x is equal to 3, 2 to the power of 3 is going to be 8, right? The y's are being multiplied by 2 every step of the way. Every increment, every 1 that we increase the x by, right? So the x increases by 1s and the y doubles every time, right? So when x is 3, y is 8, right? 1, 2, 3, 4, 5, 6, 7, 8. Like we're going off our grid line, right? Let's go on the negative x's, and we're only going to do, what do we got? We've got room to do one of the negative x's, right? So let's do x is equal to negative 1. Okay. X is equal to negative 1. It's going to be 2 to the power of negative 1, right? And we talked about what negative powers are in series 2, right? And negative power is just kick the, whatever's in the top down or whatever in the bottom up, right? It flips things. So this becomes 1 over 2. So when x is negative 1, y is a half. Okay. What you're going to find out is if you plug in x is equal to negative 2, y is going to be a quarter. X is equal to negative 3, y is going to be 1/8, x is equal to negative 4, y is going to be 1/16. So what's going to happen is we're slowly going to approach the x-axis. So, my graph isn't accurate enough to draw this very closely, right? But this is what an exponential function looks like. Now I got to draw a curve for this so we can get this down packed. So this thing goes like this, right? Comes up. And 1, 2, 3, 4, 5, 6, 7, 8 goes up, right? And that is what an exponential function looks like, and it always goes through 0, 1, irrelevant of what the base number is. If this was a gazillion, y is equal to a gazillion to the power of x, a gazillion to the power of 0 is going to be 1. So what's going to happen if this base number, for this number 2, if we change it to a bigger and bigger number, all that's going to happen is this graph is going to get tighter and tighter, and this is going to get closer over here, going to be sharper drop to the x-axis. Okay, and what happens is the x-axis becomes an asymptote, right? Because this thing keeps on getting closer and closer to the x-axis, but it never touches it, right? Because we can't set x equal to something to make y equal to 0, because that's basically our y equals 0 line, right? So this is what a basic exponential function looks like, our most rudimentary exponential function that we have. Okay, now what we do in mathematics is we like to see how things play out. We like to change things around and see what happens to a system, right? And one of the things we do in mathematics, we flip the position of the x and y. I'm not sure how this came about. Okay, some mathematician was probably sitting there, working on their desk or working, wherever they were working in nature or whatnot, and they looked at an exponential function, y is equal to a number to the power of x, and they asked themselves, what happens if I switch the position of the y with the x, right? What happens if I create a new function that the equation is, should we do this in blue? No, we don't want to do this in blue. Let's do this in green. Okay, let's do this in green. What happens if I switch the x and the y, right? What happens if I go x is equal to 2 to the power of y? Okay, I hope you can see that. That's big enough. I think so. Okay, what happens if I do this? Okay, now what we need to do to be able to represent the function, we have to get y by itself, right? And to be able to do that, we need logarithms. That's where the logs get introduced. Okay, because the y is to the exponent right now, and we need to have y by itself. We need to get y on the base level equaling something x, right? Now let's graph this thing using table of values again, just the way we did here, right? But because it's going to be extremely hard for us to plug in values for x to find out what y is, random values, what we're going to do is we're going to take these numbers for what we did for the x and plug them in for the y and find out what the x is going to be, right? We're going to switch positions. switch roles, right? So we're going to have a table of values. Again, we're going to have x and we're going to have y, right? Now, instead of starting out plugging in numbers for x and calculating what y is, we're going to plug in numbers for y and calculate what x is, right? So let's do y is equal to -1 first. Or should we do y is equal to -2 first? Let's do y is equal to -2 first because we didn't do it here. So you get a nice grasp of it, right? So y is equal to -2, right? So this is going to be 2 to the power of -2. So it's going to be 2 to the power of -2 is going to be 1/4, right? If you do y is equal to -1, this is going to be 1/2. If you do y is equal to 0, 2 to the power of 0 is 1. So x is going to be 1. And there's something you should have noticed right now. We switched the position of the x and y, right, from the original exponential function to create this guy, this beast, I guess if you want to call it, right? So if we switch the position of the x and y, what we're really doing is switching the x and the y values, right? So if we go 2 and 3, well, if we go 2 and 3, those are these values, right? So this becomes 4 and this becomes 8, right? Our x and y have flipped, right? That's what we got here. We switched the x and the y position, okay? So if we're going to end up graphing this, when x is 1/4, y is -2. When x is 1/2, y is -1. When x is 1, y is 0. When x is 4, y is 2. 1, 2, 3, 4. Y is 2. When x is 8, y is 3. I don't know if we can go as far as 8. 1, 2, 3, 4, 5, 6, 7, 8. We're, at the edge of the graph paper. We're off the graph paper. So that would be 3. When x is 8, y is 3, right? So the graph of this looks like this. And what happens is, for a logarithmic function, as the y decreases, it becomes, the y-axis is asymptotic, right? It gets closer and closer to the y-axis as it goes down, but it never touches it, right? And this thing, as x increases, y continues to increase forever and ever and ever, right? And what we have here, okay, this is the graph of a log function. And what we do, what we say we've done, when we switch the position of the x and the y, right, what we're really doing is reflecting a function on the line y is equal to x, okay, on a line that goes at 45-degree angle this way. So that's what we're really doing when we're dealing with logs. Logs are the inverses of exponential functions, right? So if we do sort of a mirror line here, if we continue to go down, okay, this red line is the line y is equal to x. Okay, that's the equation of a line. Our y-intercept is 0 and our slope happens to be 1, so we go up 1/1, right? Hopefully this is dark enough that you can see it. Let's draw this a little thicker. Okay, so our y equals x line becomes our mirror, right? So what we've done here is, if you can think about it, this is the way I like to show it. You take the y equals x line here, and this graph that we have here, the exponential, all we've done a little flip, and we've created the log graph, right? And we can take the inverse of any function, right? If we have anything that goes through here, we can take this line, put a line here and go, and the thing flips, okay? That's what a log function is. And if you want to look at it with the point system, with the coordinates, all of these coordinates, all we've done was we switched them, right? When we take the inverse of an exponential function. So what we've done is, if we take the inverse of this point, we switch the x and the y, so this point becomes 1 and 0, okay? This point here, let's put in the points, let's put in some of the points anyway, right? Let's say this point here is, the x is -2 and the y is 1/4. That point here becomes, we switch them, it becomes 1/4 and -2. This is the point here. That point gets flipped here, 1/4 and -2. This point here is x is 2 and y is 4, right? 2 and 4. If we switch them, if we take the inverse of it, it becomes 4 and 2, right? So 1, 2, 3, 4, and 2. And 2, right? We just switch the x and the y's. And we do this, you know, before we do logs, usually in grade 12, what we do, we deal with, we introduce inverse functions first, right? Because that way the concept of taking the inverse of a function, you know, is stuck with you, right? You understand what the concept is. And then we take inverses of exponentials and we get our logarithms, right? And for us to be able to take this function, x is equal to 2 to the power of y, and isolate the y, which is what we really want to do in mathematics, right? The y is our function, is our dependent variable, and the y is dependent on what the x is, right? That's sort of the concept of functions which we're doing in series 4, right? Or we're building up to it, right? We will be hitting it up, right? And talking about what functions are. But functions are basically an dependent variable taking a look at what happens to something that is dependent on something else. And our dependent variable happens to be y, and our independent our dependent variable happens to be y, and our independent variable happens to be x. So the way we want to represent this, we want to get our dependent variable, what y is, by itself on one side, equaling whatever is dependent on, which happens to be our x right now, right? So the question here is, how do we get y by itself, right? And to be able to do that, we need logarithms. Okay, we need the concept of logarithms. And logs works the same way, in large part, conceptually anyway, the same way that exponents work, right? Exponents have rules that we have to abide by, right? If you multiply two numbers that have the same base and different powers, you end up adding the exponents. Well, logarithms has something, a rule similar to that, right? If you're dividing them for exponents, you subtract them. Logarithm has something similar to that, right? We're not going to go into the log rules right now because I do want to build up to that. But what I want to do is show you how we get y by itself here. And there's a shortcut way and there's a longer way. And we'll do the longer way, but I'll show you what the shortcut way looks like too, right? So what we end up doing is, let's do this here. Okay, it's very simple, but you have to know the log rules to be able to do this. So let's say we had our x is equal to 2 to the power of y, right? And we want to get y by itself. So what we end up doing, we end up taking logs of both sides. And remember, for an equation, basically the concept of equation is a balance, right? A scale, right? So if you do something on one side to make sure everything balances out, you have to do it to the other side, right? So we're going to take log of this side And if we took the log of this side, we have to take the log of this side. So this becomes log 2 of y. Okay, and whenever we we'll get into this, but whenever we write log, it's log to the base 10, right? Now, there's a rule in logarithms that says if you have log of something to a certain power, you can take that power and put it up to the front, right? You can drop it down. So if this is this guy, let's do this in red, the y can drop to the front. Okay, so this turns into log x is equal to y log of 2. Now what we want to do to get y by itself is really simple right now. All we got to do is just divide this side by log of 2. And log of 2 is just a number, right? It's just, you punch in your calculator and you find out what it is. So we're going to divide this side by log 2. I'm going to divide this side by log 2, right? So right now, this, let's do this with green, that kills that. So we have y by itself. So we've got y is equal to log x over log 2, okay? Now, in logarithms, we have another rule, okay? Another way that we can simplify things. And that's by saying that if you have a log of something divided by the log of another thing, as long as they have the same base, the log, you can merge them together, put them together, and it becomes y is equal to log base 2 of x. Okay, so these two merge together, and what you're dividing by goes into the base of the log. So this is our logarithmic function, right? When we take the inverse of this. Okay. So this guy is the inverse of that guy, right? This is a log function. That's an exponential function. And this is the inverse of that, and that is the inverse of that, vice versa, right? And what that means is we've taken a graph, a function, and we use the line y is equal to x as a mirror line, right? And we've flipped it, right? I mean, just imagine if you had this as a mirror, right? Let's assume this pen was a mirror. If I was standing here, right, my reflection in the mirror would be over here, agreed? And if I came up and touched the mirror, my reflection on the other side would touch exactly the same location as I'm touching it over here, right? Let's do this like this, right? That's what this mirror line is. Our graphs don't happen to be touching the mirror line, but they're the same distance apart, right? So if you go perpendicular to this, right, that's sort of, what we have. The distance from there to there is the same as distance from there to there. I believe so anyways, the perpendicular, right? And the distance from there to there is the distance from there to there. Distance from there to there is the distance from there to there, right? That's what a logarithmic function is. So when you're doing logs, keep this in mind, really important. Conceptually, it's not very difficult. It's just the mechanics of it. To be able to simplify log functions that really burns people for the most part, because it's a new concept that everything comes to you in one chunk, where learning the exponential rules, those are presented to you over a number of years. In grade 8 you see them, grade 9, grade 10 you delve into them, right? So over a 3-year period it's sort of giving you slowly and piecemeal. But in grade 12, because you're in grade 12, you're dealing with logs, so all those rules come to you in one shot. So you have to learn how to manipulate a log function or expression using those rules really well, right? As far as getting this in one step using this function, so what we can do is let's say we got the same thing, x is equal to 2 to the power of y, right? What I usually do, instead of going through this whole shebang, right, and this is sort of going through every step to get that function, you know, what I end up doing is, or what you can do is, take the base here, right, the 2, you kick it down to the base for the log, and the y drops. Okay. When that happens, this goes to the base of a log, so this becomes log base 2 of x is equal to y, which is the same thing, right? Y is equal to log base 2 of x. But that's the way I usually, you know, once you understand what's going on here, that's the way you can, you know, do it short, you know, the quick way, really. Okay, so keep this in mind. This is it's an important concept, and it's beautiful. I really like logs. I know when I learned it in high school in grade 12, I had a hard time. I had a hard time with trig, and I had a hard time with logs because I couldn't visualize them. I didn't really fully grasp them. I guess because when I was being taught, they were just telling me, you know, these are the rules, this is what you do, and you know, monkey see, monkey do, right? And that's the way I was taught mathematics in grade 12. But I think it's pretty important to be able to visualize it, right? To be able to understand what's going on, and we will expand on this a lot more. I do plan on creating a whole module for logarithms, just the way we are for trigonometry, because it is important. It's powerful, and it comes into play in science a lot with the Richter scale, with the pH scale, and I am a geophysicist. Well, that's my education anyway. That's what I trained, and that's what I did. So we dealt with logarithmic functions a lot, and you do deal with exponential functions a lot. Really important to understand what exponential growth is, right, and what exponential decay is, right, and how logarithms come into play in this, in the real world. This is one of the most important concepts that we really do have to understand to be able to function properly in the world, right? What are exponential functions? What is exponential growth? What are logarithms, right? They model a lot of systems, a lot of important systems. Okay. I hope I didn't go too quick on this. Just an introduction on log, just so you can get a visualization of what logs are. Okay, and we'll hit this up hopefully towards the end of 2016, maybe 2017, with you know, going through every step and taking a look at the log rules and how you can manipulate expressions and functions.